Mass defect and binding energy of a nucleus. In the nucleus, neutrons and positive particles, protons, are forced to stay together. In reality, they want to move apart from each other. What is the source of the energy that keeps the nucleus from breaking apart? Searching for a possible solution, scientists measured the mass of a helium nucleus, one of the basic natural chemical that we have. They also measured the mass of individual protons and neutrons. Then they added all together. Scientists predict the measured masses should be the same, but this is not what they observed. The sum of individual masses of protons and neutrons is greater than the mass of the helium nucleus. Where is the missing mass? Turns out this missing mass is converted into the required energy to keep the nucleon, which is protons and neutrons, without breaking apart. To understand how the mass is converted to energy, it is important to note that we are using the masses in atomic mass unit, or U, for our practice problems. Here we have the mass of electron, proton, and neutron in kilograms. And here it is showing the same mass, but in scientific notation. This is the mass of a proton and neutron in atomic mass unit, or U. And this is the formula of mass energy conversion from Einstein, and the C is the speed of light squared. M is the mass, and E is energy. So on your page 58, just follow me and complete the blanks. Nucleus are made up of protons and neutrons, but the mass of a nucleus is always less than the sum of the individual masses of the protons and neutrons which constitute it. Scientists believe the difference, the missing mass, is a measure of the binding energy which holds the nucleons together. This binding energy can be calculated from the Einstein modified formula from original. The nuclear binding energy with the modified formula will be E is equal mass times 931 mega electrovolts per U. So this M is a prefix. Binding energy is the energy required to split the nucleus apart. That's the minimum energy that we need to break a nucleus. In the bottom section, we are going to learn the steps that we need to take in order to calculate the binding energy of a nucleus. You need first to find the number of protons and the number of neutrons of the chemical element that we need to calculate the nuclear binding energy. So let's start with define the mass defect or the mass difference. When you have the number of protons, you multiply this number by the mass of a proton in U. You do the same with the number of neutrons times the mass of neutrons in U. Then you add the total masses of protons and neutrons, and then you subtract the added masses of the nucleon, which is protons and neutrons, with the mass of the chemical element that was given. So this difference is called the mass defect. Now, to find the binding energy, you need to use the formula, that Einstein formula, modified one. Step 4, this is the mass defect times 931 MeV per U. So here is the mass of a proton in kilos, in atomic mass unit, or U. This is the mass of a neutron in kilos, or atomic mass unit or U. So this is the data that we are going to need to solve two practice problems. Let's go to our first one. Calculate the mass defect and binding energy per nucleon for each atom on the table below. So let's start with helium. The number of protons for the helium is indicated at the bottom part of the chemical formula. In this case, is 2. The number of neutrons is the top number minus the bottom number, which is 4 minus 2. By coincidence, is the same. Number of neutrons is 2. So the total mass of protons is 2 times the atomic mass unit, or the mass of a proton in U, which is this number right here. When I multiply this number, that's what I have. The total mass of a neutron, 2 times the mass of a neutron in U, and that's what I have. Now I'm going to add both masses, and that will be the total mass of my nucleon when I calculate separately. Now the element mass is given, is right here. The mass of a helium nucleus can be found in a periodic table or any textbook. So in this case is 4.001509 U. We are trying to keep with 6 figures after the decimal. Now when I calculate the mass difference, which means a step 5 minus 6, the difference is 0.030373 U. So I'm going to use this mass difference or mass defect to find the binding energy by using this formula. So the mass defect times 931, and when you do the math, you have, now we can round for just 1 decimal, will be the total energy in the nucleus is 28.3 MeV. So now, what is the contribution for each nucleon for this energy? To find out, you have to divide by the number of nucleon. So how do I know? The number of nucleon is usually here on the top of the chemical element, because this is the number of protons plus the number of neutrons. In this case, it's 4. So it will be 7.1 MeV per nucleon. So each nucleon, each proton, and each neutron make this contribution to keep them together. So let's do now the second problem. It's the same from the previous one. We're going to do one more practice. So number of protons, you can pause the video and try to do by yourself, or just follow me along with the lesson. So number of protons is indicated here at the bottom, 8. Number of neutrons is the top minus the bottom. In this case, again, is by coincidence is the same 8, 16 minus 8. Total mass of a proton, so number of protons times the mass of each one. So that's what I have. Total mass of neutrons, same process that we did previously. Now total mass of nucleons. Nucleons, I have to add those together. Now the element mass given. So that again was given in that previous page. So just look at the bottom of the page, you should see this number right here. Now the mass difference is when I subtract the top number minus the bottom one. So I have this number. That's the mass defect or mass difference. So the binding energy is the mass defect times 931. See, very simple. And we have 118.6 MeV. And the contribution for each nucleon, I have to divide this number by the total number of nucleon, which is indicated here at the top of the chemical element, 16. So 7.41 MeV per nucleon. So on the next page, you can complete your atomic physics vocabulary. And How we can use this? Well, scientists found a way to break these nucleus apart by shooting a bullet, which is a neutron, very kind of high-speed neutron, break the nucleus apart and release some of that energy. So how can we use that? We can use this energy to for in nuclear power plants or atomic bombs. So that's the end of the lesson. I hope you have enjoyed and complete your work. Thank you very much.